I'm in the infrastructure team, so I'm doing the internal or helping with the internal tooling like Jenkins, Docker, Amazon, packages, everything people need. And I'm also out doing lots of talks while I'm not at home doing work. So I'm not sure if I'm doing work today or if it's just fun for me. But yeah, this is what I'm doing. Otherwise, in Vienna, I'm running a database group. Just everything you want to do or to know about databases in general, both relational and non-relational. And I'm also running the local Papers We Love group, where we read academic papers and discuss them afterwards. So this talk is kind of all these things mixed together. So we're covering databases on the one side, and on the other side, we're starting off with a little theory. Don't worry, it won't be too much. And then we'll dive into the actual stuff. OK, so let's get started with databases. The way we think about databases today is very different of what we thought about them like 10 years ago or probably 30 years ago. And the initial start of everything was 1970. The original paper, a relational model of data for large shared data banks by Cod, which was the paper that changed the view on how data is organized and how data should be structured and queried upon. And the gist of the paper was basically you have a relational model and normal form. So this was kind of the math part you have behind of it, how it's actually the data should be structured. And from that on, you have data independence. And the data independence back then was a very novel idea, because every database vendor had kind of their implementation. And to interact with that database, you had to actually know how the data was structured internally. So you had some very low-level API you could interact with, and you really needed to know, like, how is the data stored and how can I query it? And that was very much specific for each of these database products. And Cod then said, well, this is actually a bad idea. Let's find one theory we can structure our data in, and then I don't really care about all the low-level stuff, like how are you actually storing the bits on disk. I don't want to know, I don't care. I just want to have a nice model people can use, and then you don't need to care for the internal implementation details. And that led to the kind of data independence people wanted. The theory looks a bit more complicated than you would expect. So at the bottom, the SQL query, you will probably easily understand, select name from people where died at age is null. So all the people that have not yet died. And what Cod actually did is he didn't define the SQL. He defined that. That is what his paper kind of defined. Like you define a free variable with name, and there exists a tuple with name and died at. And that is in the total people available. And there is a tuple where died at age is empty. And for the same name from that tuple and the people, that matches together. So this is kind of the theory, what is going on behind the scenes. But luckily, you don't really need to care about that too much. You have SQL, and you can simply use it. But you don't need to know how it's actually the mathematical part behind it. And based on the mathematical part, again, guys from IBM thought, well, we need a nice language to interact with that, and that's why they started SQL, a structured English query language. So this was the original name for SQL. But then some company had for SQL, there was another product that nobody knows. I don't even think it was in IT, and it's no longer available. But because they had the trademark on SQL for that, SQL had to be renamed. And they just threw out some letters, and then it was SQL. But that is the kind of theory why originally it was SQL, and that's why many people still say SQL, even though it's just SQL at the moment. What they did is you have something declarative, and the implementation details you really don't care about. So you declare something, and then you have the query optimizer inside the database that does the actual heavy lifting, and you don't need to care about it. And there are fascinating papers and even very old websites where they discuss how they actually invented their SQL language. And they had lots of discussion how to name stuff. So the discussion if it should be null or whatever that data type should be, it's a fascinating history, and you can actually read up on it that there were big arguments about what to do. But back then in the 70s, they kind of decided what SQL should look like, and that's what many people are still using today. Okay, and one other thing you can see in SQL that was also built for user interaction. So back then you didn't have your fancy websites, think about 70s, 80s, and suddenly there was something that was very simple. So SQL was very simple in comparison to what else you had. Otherwise you would need to write a custom product, but with SQL, everybody could kind of query their data. So stuff that was built into SQL very much reflects that idea that just everybody could query the database and get the data that they actually want. So you can do aggregates. This is one very common feature. And stuff you don't want to care about is like concurrency, integrity, consistency, and type safety. All of this is handled by SQL, and you don't need to care about it because it was deemed like if the secretary is just querying some data, she can do that with SQL, but she doesn't know about concurrency, and she doesn't need to care about it because SQL will take care of that. So that was very nice, and everybody started using the products. And yeah, like Dilbert always says it best, people started to write their databases for themselves because they said, yeah, this is going to be great and this is helping us. But many people didn't really know what they were doing. And we can probably see that with the NoSQL movement again, but back then it was kind of the same. And COD, who originally defined the model behind it all, saw that many people, because relational databases became very popular and fancy back then, that people were using some different products and then just implemented some very minor relational part on them and then slapped the label relational database on top of them, even though they were not really a relational database. And he actually wrote another paper, which was called COD's 12 rules, even though there were actually 13, because like every good person in IT, he would label them from 0 to 12. And if you actually wanted to be a relational database, you would need to adhere to all these 12 or 13 rules. And only then would you be considered a relational database. And this is also the reason why relational databases, even though they are kind of different in what we have today, they all share very much the same ideas and concepts which are underlying there. Partly because COD very well defined, you need to do these things and you don't or you must not do these other things to be a relational database. So their understanding of what a relational database is relatively strict and well defined. And then, like in the 70s, 80s, we had a wide variety of databases, and then we kind of fell into a dark age of databases, which looked like something like this. So you had the big guys like Oracle, DB2, SQL Server, and then some others who are probably not around anymore. But these kind of took over the market, and you had like many different products in the beginning, and then just a few big players were left, and all the others were either bought up or, yeah, just vanished into the void. And Uncle Bob, I guess many will know Uncle Bob. He writes lots about unit testing, and he has his paid podcast and stuff. He is very vocal in the Java ecosystem. He wrote a very nice blog post about databases, and he compared the development of databases to beer. That in the 1920s, when you had the prohibition in the US, people in America actually lost the knowledge on how to produce proper beer. And once the prohibition was over, you had just stuff like Bud Light and terrible beer in the US. So this was kind of the dark age, and he compares it to the dark age of relational databases, that in the beginning, many people were developing their relational databases, and then just a very few were left. And this knowledge on how to build databases actually was kind of lost. And sometimes in the 80s, 90s, and later on in the US, people started their microbreweries, and now you can probably get proper beer in the US again. And we'll later see, like for databases, the NoSQL world kind of rediscovered how to actually write new databases, and then you had this explosion of new NoSQL databases. But why did we actually see the need for NoSQL databases. The first one, I'm not sure if it's true, but you can always argue about that here is a relational database, and that is your application. And your application on its own could go much faster than with the database. So the inflexible and slow turtle is holding back the fast dog, and this is kind of database application. And many people had this feeling that my application is being held back by the slow database, and it's not up to its needs. So we need something else. The only problem, speeding up is hard, and I think this is the last paper we're taking a look at, is the consistent, available, and partition-tolerant web services. Even though web services might be misleading, this is just for any distributed system. So it's probably very well known as the CAP theorem, actually defined by Eric Brewer, but Seth Gilbert and Nancy Lynch wrote the paper. And what they defined is you have these 3 properties you want to have. So you want consistency. Consistency at one point in time, you have one view on all the data. So if you have your data on many servers, at one point in time, you want to have the same data on all the servers. And you want to observe all the same data on the servers. The second one is available. All nodes, as long as they are reachable from the network, should be able to participate in queries and actually respond to queries. And finally, partition tolerance. You have your distributed system, and bad stuff might happen, like the network break in the middle, or you have a big garbage collection and your nodes are not responsive. You just don't know. Stuff is not responding, and you don't know if it's broken, if it's just waiting, it's dead, will it come back, it won't come back. But still, even in these scenarios when you have a network partition, that your network is breaking probably into different parts, you want to be able to still answer queries. And unfortunately, what they prove in their paper is that of these 3 properties, you can have at most 2. So if you design your system badly, you might just get 0 or 1 of them. And if you do well, you will get 2. So you can be either here, here, or here, but you cannot be here in the middle. It's just not possible. And the proof is very systematic, actually. It's not, you don't need lots of math. It's just, imagine you have 5 nodes, and the network in the middle between the 5 nodes breaks somewhere. So on the one hand side, you have 3 nodes, and on the other side, you have 2 nodes. And they cannot communicate with each other. And then what you want, you still want to write data. That's the partition tolerance. Even though your cluster is in a bad state, you still want to write data. And then you can decide, can I write data to one part of the network? If yes, your system is available, because even though it's broken, you can still write data. So assume you write data to these 3 nodes on the one hand side, and they have successfully written it, but you have broken consistency, because the network is broken in the middle. So if you query the nodes on the other side, you cannot get the current data, which is kind of very intuitive. So if stuff falls into 2 parts and you can just interact with one part, you need to decide, like, do I still want to interact with that one part? And then the other one won't be in a consistent state. So it's actually pretty easy to understand. The only thing that might be confusing is that consistency in the CAP theorem is different to consistency in ACID. So in the transactional way, the consistency there is like I go from one consistent state to the next consistent state. So I don't break any predicates, like not null constraints, references, all these constraints you have in the databases. This is what you would have in the ACID consistency. And the CAP theorem is about timing. So at one point in time, you have one view over all your nodes. And if you have children, or if you want to explain this to your not so technical colleagues, Robinson Crusoe is a very nice example. So you have Robinson Crusoe sitting on his island, and I think he's English. So he's sitting on his island, and he doesn't know what is going on in the world. And so since he's on his island, he's partitioned from the rest of the world. And now assume a ship comes by and asks him, who is the king of England? And he's from England. And he doesn't really know. And then he has 2 choices. Either he can be available and answer, but his answer might not be consistent because he doesn't really know. Or he might be consistent, but he's not available because he doesn't answer. But then he's consistent because he's not giving out the potentially wrong answer. And there's this thing, eventual consistency, that at some point your data will catch up and be up to date. And that would be the message in a bottle he would probably receive every few months. And with a hefty delay, he would probably still know who's the king in England, or was the king in England like a few months or weeks ago. So this is kind of the story to explain the CAP theorem. And then people always say, yes, but my network is doing so well, I don't have network partitions. And this is normally not true. I mean, you can always claim it to be, and it will probably work for a long time, but at some point, stuff will fall over. There's this guy, Kyle Kingsbury. His Twitter handle is Aether, and his website is Aether, and he now professionally breaks databases. And one thing he wrote was why this is actually not true, and he made a huge list of stuff where the network broke, and you had, for whatever reasons, the consistency even within a single data center or the network, non-network partition could not be guaranteed. And he wrote all these facts together, and every time somebody says, hey, my network doesn't do bad stuff, point him to that and say, yeah, actually, it probably will at some point. Don't rely on it too much. OK, so this is the one part that's playing into the whole NoSQL world we'll come to in a moment. The other one is about the schema flexibility. So the relational world is very rigid about the schema. And you can relax stuff more. So depending on how far you want to push it, the first level would be you don't have any structure at all. So you'd simply have bytes on your disk. This is probably not that useful. But where stuff starts getting useful is key-value pairs. So you have a key, and you can only look up the key. And from that key, you can actually get the value that is stored. Just think about it, that if you know there is some value, but you don't know where it actually is or what the rest of the value is, you cannot query it. So you can only query the key part. This is kind of the big problem, which you're not really used to in the relational world, because as soon as you have something in your table, you can query the column wherever the data is. And yes, indexes will make that faster, but even without an index, you can query the stuff. With a key value store, that's probably not true. The second part would be, yes, you have some more structure. And here we put everything in that doesn't have a rigid structure, but like, yeah, some stuff or another. So you have, for example, the graph databases where you have nodes, and then you have the edges between them, and you can easily traverse those. Other would be document stores. Since JSON is all the rage, everything needs to be JSON at the moment. So you can store and query your JSON documents in there. Or you have stuff like column-oriented databases like Cassandra, where you have, it looks like a table, but it's not really bound to that because you have different versions or timestamps of your data. So it might be not really a flat table, but more like a three-dimensional table. But that data structure is also somewhat similar to what you would expect in tables, but not entirely. And then finally, you have something with a rigorous schema, like relational databases. So every column you have needs to be there. Even if you don't have a value, you need to put a null value in it. You cannot simply leave one column out. However, what you get is you get stuff like joins normally. And that is not very common in the NoSQL world. OK, so NoSQL. Actually, it doesn't stand for NoSQL, but not only SQL. Even though some people claim that how the name came about, that you had the recruiter who wanted to pimp up your CV, and you didn't know SQL. So they simply wrote, you're an expert in NoSQL. And I'm not sure if that's true. Actually, no, it's not. But it's still, recruiters might do stuff like that. And then there are people who say, yeah, with this big data thing, and this is all very nice. And it is big data, it lives in the cloud, and it knows everything, and you will be able to make lots of money with it. The thing is, with big data, so often the question comes like, is big data equals NoSQL? And like there are two different views on that. The first one is very broad, that big data includes everything where there is lots of data. And that probably includes what people call NoSQL. But Other people make it a bit more or a narrower definition where they actually say big data is mainly for offline data or data warehouses. So if you have stuff like Hadoop and Spark, this is what big data means. But every time somebody says big data, blah, blah, I'm a bit like, yeah, big data is a big buzzword, and stop saying big data too much because it's not meaning all that much. It's mainly a buzzword people throw around. Okay, and then there is this stuff like how popular are all these databases? And depending on how much you believe in these ranks, pretty much like the ranking of programming languages, they give you kind of an overview. So Oracle is still very popular, even though MySQL is catching up a lot. And then you can see also the NoSQL databases are entering the database rank. So you have MongoDB pretty high up, you have Cassandra pushing stuff, you have Redis and Elasticsearch. And so these are the ones we'll take a look at. And from the relational world, I have just picked Postgres because it's also pretty popular. Okay, so let's dive into it. MongoDB is a document store, so it's basically you throw JSON at it, and then you can query the JSON and get JSON back, which is very convenient if you have JavaScript, for example, and you have JSON anyway, and you need to transfer JSON, that it was what MongoDB can give you. And one other thing I always very much like is that object relational mapping with relational databases is not always going that well, and Ted Neward coined it, ORM is the Vietnam of computer science, so it's not going all that well. I mean, he wrote that blog post 10 years ago, but it's still somewhat relevant, and he has multiple points on stuff people do or need to do to break the paradigm just because ORM is too limited and doesn't really give them all the stuff they need. So who has used JPA and seen stuff like this? Who has written stuff like this? Do you think this is okay? No? Yeah, some people say I'm okay. But you're probably in denial. Or it's like the Stockholm Syndrome, where you kind of given up, and then, yeah, you're with your captor, you're on good terms, actually. So let's think about a very simple example. So you have an abstract base class, like an employee, and then you have a manager who can approve funds, and you have workers, and workers have experience. Obviously, managers don't have any meaningful experience. But that's their problem. So you want to put that into a relational database. And in the relational world, you actually have three options. The first one is you simply use a union table. So you have a table with employees and potentially many null values, which works. And for that example, it's probably fine because you just have two attributes which are different between the specific implementations. But if you start to have more implementations and you start to have many attributes, your relational database will start to look like a Swiss cheese because it has more null holes than actual data. So this is probably not the best way for bigger or stuff where you have many implementations and attributes. The second option would be you have concrete instances, but then you wouldn't have common queries or like no simple common queries. So you would have a manager table and a worker table, and you would have all the data in them. You would have some schema information duplicated, but let's assume that's fine. The main problem starts when you start, okay, just give me the names of all my employees in my system. Yes, you of course can do a union query and unionize all that data together, but still it's not really that nice. And you can see, okay, whereas in the object-oriented world, this comes very natural that you have specific implementations. The relational world is not really geared towards that distinction. And the final option would be you structure your tables just as you have your code. So you have the abstract base class as one table, and then all your specific implementations are tables as well. However, whenever you need to query a manager or a worker, you would need a join. And again, yes, it somehow works, but it doesn't really seem to fit too well. And with MongoDB, this is just a Java example where I'm just using some annotations. You simply say, okay, this is my base class. I have some stuff like an object or an ID in it. And then my concrete implementations, I don't need to change anything. And what you would actually get in your document store is just the stuff you have. Since you don't need null values, this is just the objects you would have would pretty well map down to the document level. And this is true. Everything that stores JSON could use something like that and does it similarly. So this is not really limited to MongoDB, but it's the most common example. But CouchDB, Couchbase, Elasticsearch also storing JSON, all of them kind of would do it in a similar fashion. You don't really have this divide between objects and relations. With documents, that fits the object-oriented model much better. The main drawback with MongoDB is it's super popular, and as long as you only need replication, it's working very well. We don't need to go into all the details. Just as replication is easy to duplicate your data, so if you lose one node, another node can take over and will just start serving your read and write operations. The only problem is MongoDB has a model where scaling out is a bit hard, because you have this here is one replica set. So here you have one node where all the reads and writes go. That would be the primary. And then you would have the secondaries. And these cannot take writes. These can only do reads, which might be slightly outdated. And if you then discover, like, OK, I need to scale this up, so from 3 nodes, you suddenly need to have more nodes. So you think, I want actually 3 servers which can actually handle write operations. And then you would that is one who can do write operations, and you would have 2 replicas with it. This one could do write operations, and again, 2 replicas with it. This one could do write operations, and again, you have 2 just doing for the replication and potentially read operations. And then you have the routing component, which will just know, OK, to which data to query to get data. And then you have config service, which actually know where the stuff should be stored and tell the routing service where to go for each query. So you need many different moving parts and potentially many nodes. So scaling out MongoDB is not all that trivial. OK, next up, Redis is basically a key value store and much more, and adding more and more features. Originally, the name Redis comes from remote dictionary server. So if you're from Python or so, every array, list, whatever, is a dictionary, and you could simply store that in Redis. So you don't have just key value stores, but you have stuff like, it's called sets, sorted sets, and lists. You can store these in Redis and query them. So it's much more than a simple key value store. But what we take a look at is statistics. For example, assume you have a website and people log in. And you want to know who logged in during the last hour into my server. And for that, you could use 2 data structures which are supported. The first one is a bit set, and the second one is a hyperlog log. So assume you have a bit set, and your users sign up. So you have probably a unique user ID, like this was the first user, this was the second user. Think of it like an auto-incrementing key. So you simply know, OK, this user who is currently logging in is the 5th user that has ever signed up to my server. And you would assign the 5th bit to that user. So you have just for every hour, you initialize a huge bit set, all with zeros, so nobody has logged in. And as soon as somebody logged in during that hour, you would flip the bit and say, OK, this user has actually logged in during that hour. And so for 1 million users, you would just need 123 approximately kilobytes per hour, which is totally reasonable to keep in memory on your server. So this is kind of the exact approach. You simply flip the bits. This user has logged in. And the other data structure is a hyperlog log, which sounds very fancy. And yeah, again, there's a paper, and you can read the paper. What hyperlog log basically does is if you have unique elements, so users are unique elements, you can store them in 12 kilobyte regardless of their actual number. However, the trade-off is this is only a probabilistic data structure, so you will have some error rate. So 99% of the hits you can have are exact, and you can then look up like, has this user logged in? And with a 99-something% correctness, you can say, yes, this user has logged in, or no, he hasn't logged in. The big advantage is it just uses very little data. So 12 kilobyte, about a 10th of what the exact data structure would need for 1 million hits. And that doesn't grow. So within those 12 kilobytes, you can just store all the data you want. So hyperlog is nice because it has constant size. Bitsets have the advantage that they are, on the one hand, exact. On the other hand, you can easily aggregate them. So after a week, you say, I don't care if they user logged in a specific hour. I just want to know, has he logged in during that day in its entirety? You simply could or connect all the bitsets per hour you have, and then you would know, okay, these users have logged on that day or they haven't. And you cannot easily do that aggregation with hyperlog logs. So this is kind of two common use cases and stuff Redis can do for you. Overall, Redis is super simple. It's definitely the simplest NoSQL database that is commonly used and that you can run. It is kind of the omnipresent glue, so I assume many of you are already using it for caching or storing some rather short-lived data, even though it's not really suited as the main data store that well. For that, you could potentially use Cassandra. So Cassandra is kind of making fun of Oracle, because the Oracle I think Oracle was in Delphi. So in Greek mythology, the Oracle, they would just do a prophecy, even though they wouldn't know. And Cassandra, in contrast, she saw the future, but nobody believed her. So they kind of think like, we actually know what the future is. Everybody is following the stupid Oracle who is just guessing. And we're Cassandra, and we are now doing that much better. So what Cassandra is good for is both scalable and highly available read and write operations. And for that, they're doing consistent hashing. And just to give you a short idea, so you have some key space. So everything has an ID. You can self-assign that, just some meaningful ID, and you would then hash that ID. So in the top left corner, the ABC would be you have 3 servers, so you hash some data, and you have between the minimum key and the maximum key, you would just split those up in 3 distinct areas, and these would map to specific servers. The hashing, of course, you could use the key directly, but then you would potentially have some hotspots. So your keys probably wouldn't be equally distributed over your whole node, over your whole key space. So you do the hashing, so those should be pretty fair, and each node should get the same share of keys per server. And then you simply start to twist the key space clockwise. This is what you get in B. So now I've just twisted my key space clockwise, and if I have one key, I would know, okay, that key, or the hash function of that key actually lands here on my ring. So it will go primarily to node A, and a backup copy will go to node B. And the nice thing about that is if you want to add more servers, you would just impact one neighborhood. Like if you want to add a server here, so you want to split up A, you would probably just add a D server, and you would just need to split up A, and B and C wouldn't actually need to do any work. And the same happens if one of your servers falls over. So if B falls over, you would simply say, okay, just throw that B is not available. So C takes over, and then actually A can simply copy over all the data it has put over to B in the first place, could copy over to C, and C would know, okay, I have the copies from B, and I can simply say, okay, I'm the primary now. And then you could copy all the data. So C copies its data to A, and A to C, and you've lost one node, but you didn't lose any data, and it's very simple to scale that up and down. You simply throw in nodes as you go. And to make that even simpler, that if one server topples over, you don't have to move around all that key space. You would normally create, it's called virtual nodes, vNodes, that you split up the ranges into finer areas and then just distribute them evenly over all your servers. So if, for example, the whatever color this is, orange, falls over, you would have just little chunks you need to move around between servers, but not this huge one. So this is a very nice model. The only thing is, Cassandra always calls itself tunably consistent, which might be a euphemism for not all that consistent. And some people say, yeah, that is actually very hard to reason about that kind of data. And there are people who say, yeah, screw that. Eventually consistent is too hard, so we went with immediately inaccurate. So yeah, I think there's someone from Cassandra here. I hope he doesn't hit me after the talk. Okay, so if you want to go for consistency, Postgres is now all the rage, and Postgres can also store your JSON now, and it's very fancy. And many people in the past said, yeah, this relational world is just too slow. And what is a common problem is that people say, hey, the relational model or database is super slow. I don't care about it anymore. I'm rewriting everything in NoSQL now, and I've created my battle plan. So I've done a big Gantt chart, and I know, okay, it will take 5 months to rewrite all of that in whatever NoSQL database you want to use. And then the colleague says, wait a minute, let me have a look. Have you added the proper indexes to your database? And it turns out, oh, if you add the right index, the relational database might be fast enough for many workloads again. So this is kind of the conclusion. So yeah, relational databases, of course, have a scaling issue, but if you use them properly, you can still use them for very many use cases. And the other thing is, relational databases is kind of misleading, since many people now call them SQL databases, because SQL, the standard you have, has kind of moved beyond the relational world, and the relational databases are also adding more and more NoSQL-like features. Like MySQL has memcached built in, where you can use key value caching. Postgres has JSON support. JSON support is also coming in MySQL, or is already here. So it's kind of, it's not only about relational databases anymore. And what is very nice about relational databases is SQL, the query language. And that's why many of the other NoSQL databases are now trying to put SQL on top of their NoSQL database, which is kind of funny if you think about the name. So we're a NoSQL database, but we try to be able to support SQL. So Cassandra has their thing that's called Cassandra Query Language, CQL. Google has the Google Query Language. Couchbase was a little more creative. They called it Nickel, but it's still the same thing. RethinkDB has Recall, and yeah, everybody tries to somehow rebuild SQL. And if you talk with the SQL guys, most of them will tell you, yeah, they're doing actually a very bad job. So the guys, for example, the Couchbase guys are very proud that they're supporting the SQL, what is it? I think the 92 standard. And if you think about it, SQL 92, that would be like somebody being proud to support Windows 3.1 because it was the same year. So sounds like a huge step back for those who have been working a long time in the relational world. So yeah, what you get is you have many features, you have lots of maturity, and you have kind of the NoSQL influence. So if you don't need to hugely scale out, because scaling out is very hard with relational databases in comparison, then this might be a good fit. And finally, Elasticsearch, since it's also very popular, even though it's not really a database, it's mostly about full-text search. So there was a talk about full-text search yesterday. Who attended? Okay, very few. Okay, I'll give you the quick overview again. So full-text search, in contrast to a relational database or databases in general, databases are very much black and white. You store data, you query data, and you get matches back. So you have exact matches and you get them back. Full-text search, on the other hand, is much more black and white. You store documents, you query your data, and then you get something back that is more or less what you asked for, and you normally have a quality of these results. So you have a score, we call it. Think of it like Google. You enter your search terms into Google, and it will give you some of these results. So it's not just about exact matches of what you have been searching for, but Google is clever enough to know, okay, this was singular, this was plural. You don't actually care about that. You're actually caring about the concept. You're so querying for the concept, and I'm giving you the concept back. So to enable that, normally what you do is you remove stuff like properties and any formatting, so you just have the text. Then you do the actual parsing. Parsing would be, okay, I have a word, and after the word there's a space or a dot or a comma. And you know, okay, this is one word, so you just get out all the independent words you have. Then you remove stop words. Stop words are just the little words that add very little information to your text, so like articles and other such stuff. They're very common, they're in all documents, they add very little value. So you simply remove them. And then you apply stemming, which is you actually want to get to the core of the word. You don't care for it being singular or plural, or you don't even care if it's an adjective or a noun. So if you search for beauty or beautiful, you don't really care about if it's an adjective or a noun, you just care about the concept of beauty, whatever. And then you can have synonyms, so you know the synonyms in your domain and you can resolve them. And that is what you actually store in your inverted index. And the inverted index looks something like this. You have your documents with whatever text there is. You throw out the stop words, you do the stemming, and what you end up in your inverted index is you have this huge list of document or of words, and then you can look up in which documents do they actually occur. And that way, you can very easily say, okay, give me all the documents where bright is occurring. And then you know, okay, documents 1 and 3. And then you say, okay, I need everything that is, I search for search and bright. And then you can just end connect. Again, these are bit sets, the bit sets. And then you say, okay, both happen in document 3. And it's very easy to query stuff like that. And this is what full text search should normally give you. And there is a pretty difficult formula just to get the score, how relevant a document is to the query you have issued. We don't go into too much detail. It's just like you have stuff like, if a term occurs in one document more often, that document is probably relevant to your search. So if you search for something and the term occurs many times in a document, that's probably a good indicator of a match. On the other hand, if you're searching for a term that is very common in all your documents, it's probably adding very little value. So that's, again, a negative factor. And putting all of these factors together, and you can boost documents and you can normalize all of it, you will get a score, and that score will actually tell you how relevant is a specific hit in the list of my terms to the stuff I've actually been searching for. And there's not just Elasticsearch, there are other products. I'm doing another talk in the afternoon about them. So if you want to know more about that stack, come to the second talk. So to conclude, there was this development of the relational world. So back in the 70s, there was NoSQL. So NoSQL was it, we have NoSQL. In the 80s, NoSQL was actually to NoSQL. In the 2000s, it was again like, no, this whole SQL thing, it's too slow and it's not working. NoSQL is the new thing. And in 2005, it was not only SQL again, like people said, okay, yeah, the NoSQL is good for some parts, but SQL is good for other parts. And like another few years later, it was no, back to SQL again, depending on how you see it. So if you're a Postgres guy, you're probably down here where you say no. Actually, it's SQL, and the NoSQL stuff was all crap. And the common question then is like, is it fast? And this is my favorite comic for that. So you benchmark two things, and yeah, one might be faster than the other. And there have been many cases where I think MongoDB, Cassandra, and Couchbase a year ago did all benchmarks with their two competitors, and each of them managed to find one scenario where they were at least twice as fast than the other two. But each of them managed to do that. So I think like most of these benchmarks are pretty much useless. Yeah. And if you don't know what database to pick, so this is a few years old, you can still see like FlockDB is in there and Couch, it was DB, but Couchbase now is probably a good alternative. And you can just go through it and find out like which database is the right one for you. And yeah, would be interesting where you land. Since we are already out of time, just two more things. First, the Elasticsearch, that is my other talk, track E at 3:30. And secondly, I have swag. If you want to grab some swag, it's up here. Just take whatever you like. Other than that, I think we're pretty much out of time. If you have questions, just come to me afterwards, ping me on Twitter, ask anything you're interested in. Thanks.